What if I told you that the most feared weapon in the Atlantic during World War II wasn't a gun, a bomb, or even a torpedo, but an invisible beam of electromagnetic energy that could see through fog, darkness, and the very curvature of the Earth itself? The Germans called it Hexengerät, the witch's device. Allied sailors whispered about it in hushed tones below deck, half in reverence, half in superstitious fear. And when U-boat commanders realized what was hunting them, many chose to surface and face the guns, rather than endure the psychological terror of being stalked by something they couldn't see, couldn't hear, and couldn't escape. This is the story of how a piece of technology transformed from a laboratory curiosity into the silent executioner of Hitler's submarine fleet. It's about the young men who operated these machines, the scientists who invented them against all odds, and the desperate cat-and-mouse game that turned the Atlantic Ocean into a technological battlefield where innovation meant survival and obsolescence meant death. By the time the war ended, this device had helped sink hundreds of U-boats, saved countless merchant vessels, and fundamentally altered naval warfare forever. But the journey from concept to battlefield supremacy was anything but straightforward. It involved brilliant minds working in secret laboratories, tragic failures that cost lives, and moments of pure chance that changed the course of history. The radar revolution didn't just help win the war, it created the foundation for nearly every piece of wireless technology we use today, from your smartphone to air traffic control systems. And it all began with a question that seemed almost absurd. Could invisible waves bouncing off metal really find a submarine in an ocean that covered millions of square miles? The answer to that question would be written in the cold waters of the Atlantic, in the smoking ruins of torpedoed merchant ships, in the desperate struggles of escort sailors fighting to protect convoys, and ultimately, in the crushing depths where hundreds of U-boats met their end. It would be written by physicists who barely understood naval warfare, by naval officers who barely understood physics, and by young radar operators who learned to bridge that gap under fire. The electromagnetic spectrum became a battlefield as real and as deadly as any stretch of ocean, and the men who learned to fight there changed warfare forever. In the early months of 1941, Britain stood alone against Nazi Germany, and she was slowly being strangled. Every day, merchant ships carrying food, fuel, and military supplies from North America set out across the Atlantic, and every day German U-boats sent dozens of them to the bottom of the ocean. The statistics were staggering and terrifying. In 1940 alone, U-boats sank over 4 million tons of Allied shipping. Winston Churchill would later write that the only thing that truly frightened him during the entire war was the U-boat peril. Britain imported nearly 70% of her food and critical war materials. If the submarines couldn't be stopped, the island nation would be forced to surrender without a single German soldier setting foot on English soil. The German Kriegsmarine had developed submarine warfare into a deadly science. Their Type 7 U-boats were sophisticated killing machines capable of crossing the Atlantic, hunting for weeks at a time, and returning home safely. Under the leadership of Admiral Karl Dönitz, they operated in coordinated wolf packs, groups of submarines that would locate a convoy, shadow it while calling in reinforcements, then attack simultaneously from multiple directions. British destroyers and corvettes did their best to protect the merchant ships, but they were fighting blind. At night or in fog, a submarine could surface within a few thousand yards of a convoy, fire its torpedoes, and dive before anyone even knew it was there. The Royal Navy had developed ASDIC, what the Americans called sonar, which could detect submerged submarines by bouncing sound waves off their hulls. But ASDIC had severe limitations. It only worked when the submarine was underwater, and U-boats had learned to do most of their hunting on the surface at night, where they were faster, more maneuverable, and virtually invisible. A submarine's low profile meant that even on a clear night, lookouts could only spot one at a few hundred yards, by which time it was usually too late. This was the context in which radar technology became not just useful, but absolutely essential for survival. British scientists had been experimenting with radio detection and ranging since the mid-1930s, initially for aircraft detection. The early systems were enormous, requiring massive antenna arrays and generating only crude detection information. They were useful for spotting incoming bomber formations, but completely impractical for shipboard use against small, low-lying targets like submarine conning towers. Then came a breakthrough that would change everything. In February 1940, two British physicists, John Randall and Harry Boot, working at the University of Birmingham, invented the cavity magnetron, a device that could generate powerful microwave radiation in a package small enough to fit on an aircraft or small ship. This wasn't just an incremental improvement, it was a revolutionary leap forward. Earlier radar systems operated on longer wavelengths measured in meters. The cavity magnetron operated at wavelengths of just 10 centimeters, allowing for far more precise detection and much smaller antenna systems. The implications were immediately recognized by the scientists and military planners who understood the technology, but translating laboratory success into battlefield reality required time, resources, and the kind of desperate urgency that only a nation fighting for its survival could muster. Britain made the extraordinary decision to share this technology with the United States, sending a technical mission in September 1940 that literally carried the secret of the cavity magnetron across the Atlantic. American scientists who examined the device at MIT called it the most valuable cargo ever brought to our shores. The moment when British scientists opened that metal box at MIT and revealed the cavity magnetron represents one of the most significant technology transfers in history, the Americans were astounded, not just by the device's capabilities, but by Britain's willingness to share such a crucial military secret. This act of trust between allies would bear enormous fruit, as American industrial capacity could produce radar sets in quantities that British factories, under constant bombardment, never could achieve. The partnership became a model for wartime scientific cooperation, with researchers on both sides of the Atlantic sharing discoveries, solving problems collaboratively, and accelerating development in ways that neither nation could have accomplished alone. The strategic situation in early 1941 was desperate enough to justify almost any gamble. Merchant ship losses were mounting faster than replacements could be built. The United States hadn't yet entered the war, but was providing critical material support through Lend-Lease. If the sea lanes couldn't be protected, that support would never reach Britain. The pressure on Churchill's government was immense. Food rationing was already severe, fuel supplies were tight, and the industrial production needed to continue the war depended entirely on imports that had to cross thousands of miles of U-boat-infested ocean. German confidence was at its peak. U-boat commanders called this period the happy time. Hunting was good, losses were light, and victory seemed within grasp. Dönitz calculated that if his submarines could sink merchant tonnage faster than the Allies could replace it, Britain would be forced to capitulate. The mathematics seemed to support him. Every successful patrol, every convoy savaged, every merchant ship sent to the bottom brought Germany closer to achieving strategic victory in the Atlantic without ever having to invade Britain or defeat the Royal Navy in a decisive fleet action. The development of practical shipboard radar grew directly from Britain's air defense network, the Chain Home system, which had proven its worth during the Battle of Britain. But applying radar to the submarine warfare problem required solving challenges that made aircraft detection look simple by comparison. Aircraft were large, flew high, and moved in predictable patterns. Submarines were tiny targets, just a few feet of conning tower showing above the water, surrounded by wave clutter that created thousands of false returns on radar screens. They moved unpredictably, could dive within seconds, and operated in an environment where storms, rain, and sea spray degraded radar performance. The first centimetric radar sets designed specifically for surface search and submarine detection began reaching Royal Navy ships in early 1941. Designated Type 271, these systems represented the cutting edge of applied physics and electrical engineering. The antenna was housed in a distinctive rotating lantern-like structure, mounted high on a ship's mast, from which it got its nickname, the Cheese. To the Germans, who didn't initially understand what they were seeing, the rotating antenna looked like some kind of navigation equipment. The men selected to operate these early radar sets came from diverse backgrounds. Many were radio operators or signalmen with experience in wireless communication. Others were electricians or technicians with a knack for understanding complex machinery. The Royal Navy established special training schools where these operators learned not just how to turn the equipment on, but how to interpret the ghostly green traces on the cathode ray tube displays, distinguishing between real contacts, wave clutter, rain returns, and equipment malfunctions. Lieutenant Commander Peter Gretton, who commanded escort groups in the Atlantic, later described his first encounter with Type 271 radar as almost magical. On a foggy night with visibility near zero, his radar operator called out a contact at 4,000 yards. Gretton ordered his ship toward the contact, skeptical but curious. As they closed to 500 yards, lookouts suddenly spotted a surfaced U-boat directly ahead. The submarine crashed off immediately, but Gretton's destroyer was able to prosecute an ASDIC attack and drive it away from the convoy. For the first time, the hunters had an advantage over the hunted in the darkness, but technology alone wasn't enough. The early radar sets were temperamental, requiring constant maintenance and adjustment. Vacuum tubes failed regularly, especially in the damp, vibration-filled environment of a warship at sea. Salt spray corroded connections. Power surges from the ship's electrical system could damage sensitive components. Radar operators became as much technicians as watchstanders, learning to diagnose problems and perform field repairs with whatever materials they had available. The learning curve was steep and paid in blood. In the early months of 1941, many convoy escort commanders didn't trust the new equipment or didn't know how to use it effectively. Some kept their radar sets switched off to preserve the vacuum tubes, only turning them on when they suspected a submarine was near, by which time it was often too late. Others didn't understand the limitations of the technology, expecting it to work miracles in conditions where physics made detection impossible. There were tragic failures. HMS Hood, the pride of the Royal Navy, sailed to her doom in May 1941 without effective radar, outgunned by the Bismarck, whose own radar-directed fire control systems helped seal Hood's fate in a battle that lasted less than 10 minutes. The lesson was clear. In modern naval warfare, the side with better sensors and better understanding of how to use them held a decisive advantage. As 1941 progressed into 1942, more escort vessels received centimetric radar, and the men operating it became increasingly skilled. They learned the subtle art of reading the display, understanding how sea conditions affected returns, recognizing the characteristic signature of a surfaced U-boat versus a fishing vessel or floating debris. They learned to vector aircraft onto contacts, to coordinate with other ships in the escort group, to use the radar not just for detection, but for station keeping and navigation in convoy. The Germans, meanwhile, were slow to understand what was happening. U-boat commanders began reporting mysterious incidents where Allied ships seemed to know exactly where they were, even in total darkness or heavy fog. Some boats were attacked before they even saw the convoy they were stalking. Others were caught on the surface recharging batteries, apparently spotted from impossible distances. The German Naval Intelligence Service initially dismissed these reports, believing the Allies had somehow developed a network of spies, or that U-boat radio transmissions were being intercepted and direction finding used to locate them. The psychological transformation among escort crews was profound. Sailors who had spent months feeling helpless, watching merchant ships explode and burn, while they searched blindly for the attackers, suddenly possessed a tool that gave them agency. Radar operators became the most critical crew members on escort vessels, their skills and judgment often meaning the difference between a successful convoy passage and catastrophic losses. The pressure on these young men was immense, knowing that hundreds of merchant sailors' lives depended on their ability to interpret ambiguous signals on a cathode ray tube. Training protocols evolved rapidly as practical experience accumulated. The Admiralty established HMS Osprey, a shore establishment dedicated to anti-submarine warfare training, where escort crews could practice coordinated attacks using the latest equipment. Mock battles against friendly submarines playing enemy roles allowed radar operators to develop pattern recognition skills in controlled conditions. They learned to anticipate U-boat behavior, understanding that submarines needed to surface regularly to recharge batteries, that they preferred attacking from specific angles relative to convoy course, that they would try to position themselves ahead of the convoy during daylight hours while submerged, then surface at night to make their approach. The technical challenges of maintaining radar equipment at sea created a new specialty within naval crews. Radar mechanics became indispensable, their ability to keep temperamental electronics functioning in hostile environments, often determining whether a ship's radar would work when needed. These mechanics developed impressive improvisational skills, fabricating replacement parts from whatever materials were available, jury-rigging solutions to problems the equipment designers had never anticipated. Stories circulated throughout the fleet of legendary radar mechanics who could diagnose problems by the smell of overheating components or the subtle changes in the sound of the rotating antenna. The evolution of radar tactics occurred through experimentation, analysis, and the hard lessons of combat. early doctrine treated radar as primarily a detection tool. Find the submarine, close to visual range, then engage with guns or depth charges. As operators gained experience, more sophisticated applications emerged. Radar could track multiple contacts simultaneously, allowing escort commanders to build a picture of the tactical situation that would have been impossible relying on visual reports alone. Ships could maintain precise station in convoy, even in complete darkness, ensuring no gaps opened in the defensive screen that submarines could exploit. One innovative tactic involved using radar-equipped escorts as pickets, positioned ahead of and on the flanks of convoys. These ships would patrol barrier lines, their radar sweeping continuously for surfaced submarines trying to get into attack position. When contact was made, the picket ship would either engage immediately if the submarine was within range, or shadow it while calling in reinforcements. This forward defense prevented submarines from ever reaching the convoy, turning what had been defensive warfare into aggressive hunting. The integration of high-frequency direction-finding equipment, Huff-Duff, with radar created powerful synergies. Huff-Duff could detect U-boat radio transmissions and provide a rough bearing to the transmitting submarine. Radar could then sweep that bearing, often detecting the submarine and providing precise range and bearing for an intercept. The combination meant that every time a U-boat reported a convoy position to headquarters or called for Wolfpack reinforcements, it risked being detected and attacked. Coastal command aircraft began receiving airborne versions of centimetric radar in late 1941 and early 1942. The ASV Mark III radar could detect surfaced submarines from ranges exceeding 20 miles, transforming the Bay of Biscay into a hunting ground. U-boats transiting between French bases and their Atlantic patrol areas had to cross the bay, a journey that previously had been relatively safe. With radar-equipped aircraft patrolling overhead, that transit became deadly. Submarines detected on the surface had perhaps 30 seconds from detection to crash dive, barely enough time if the aircraft was already close, and often not enough if the pilot aggressively pursued the contact. The development of the Lee light represented innovative thinking about how to combine technologies. Radar could detect submarines at long range, but the final attack run required visual contact to aim depth charges accurately. The Lee light, a powerful searchlight mounted in an aircraft's belly, could be switched on at the last moment, illuminating the submarine just before the aircraft passed overhead to drop weapons. Combined with radar approach, this tactic was devastatingly effective. The submarine crew would be blinded by the sudden light, unable to man deck guns or take effective defensive action in the few seconds before depth charges struck. American entry into the war brought fresh perspectives and enormous industrial capacity. American destroyer escorts, purpose-built for convoy protection, incorporated radar from the design stage rather than having it added as an afterthought. The ships were designed around the sensors, with optimal antenna placement, protected electronic spaces, and power systems engineered to support radar operations. American SG surface search radar became renowned for reliability and performance, and was eventually retrofitted to many British escorts as well. The technological competition accelerated through 1942 and into 1943. Each side sought advantages, developed countermeasures to enemy capabilities, and adapted tactics to exploit new equipment. The Germans developed METOX radar warning receivers, giving U-boat crews the ability to detect older Allied radar systems. This led Allied scientists to develop new radar frequencies and waveforms that METOX couldn't detect. The Germans then developed improved warning receivers, starting another cycle of move and countermove. The introduction of effective shipboard radar created a fundamental shift in the nature of submarine warfare, transforming it from a contest of eyesight and seamanship into a technological arms race where innovation cycles measured in months could mean the difference between dominance and disaster. This shift challenged traditional naval thinking in profound ways. For centuries, naval commanders had relied on their own eyes, the skill of their lookouts, and intimate knowledge of wind, weather, and sea conditions. Now they had to trust information coming from a machine, displayed as glowing dots on a screen, interpreted by technicians who might be 20 years old and had never been to sea before the war started. Admiral Dönitz recognized the threat faster than most German leaders. By mid-1942, he was convinced the Allies had developed some kind of detection apparatus that could find surfaced submarines at night. His staff analyzed after-action reports and patterns of Allied attacks, concluding that the British had either dramatically improved their radar or developed an entirely new type of detection system. Dönitz ordered the development of radar warning receivers, devices that could detect radar transmissions and give U-boat commanders time to dive before being spotted. The first German radar detectors, called METOX and later FUMB, came into service in late 1942. They were crude devices, essentially radio receivers tuned to the frequencies used by known Allied radar systems. They worked, after a fashion, but had severe limitations. They could detect older metric wavelength radars at considerable distances, but the new centimetric systems operating at 10 centimeters wavelength required different receiver technology. For months, METOX gave German submariners a false sense of security. They believed their detectors would warn them of radar illumination, allowing them to dive before being spotted. What they didn't realize was that the newest Allied radars were completely invisible to their detection equipment. This created a perverse situation where German confidence in their countermeasures actually made them more vulnerable. U-boat commanders, reassured by the silence of their METOX receivers, stayed on the surface longer, charged batteries in areas where they should have been cautious, and operated with a confidence that Allied radar operators exploited ruthlessly. The technological competition accelerated throughout 1943. The Allies introduced new variations of centimetric radar optimized for different conditions and platforms. Aircraft received ASV Mark III radar sets that could detect submarines from 30 miles away, making the Bay of Biscay, the U-boats' transit route between their French bases and the Atlantic hunting grounds, into a killing zone. Surface escorts got improved Type 271 and newer Type 272 sets with better discrimination and range. The Germans responded with increasingly sophisticated radar detectors and eventually their own centimetric radar systems, but they were always behind, always reacting rather than innovating. German submarines began traveling submerged during daylight hours, using their schnorkel systems to run diesel engines while remaining underwater. This reduced their vulnerability to radar-equipped aircraft, but also reduced their operational effectiveness, as submerged transit was much slower than surface travel. The psychological impact of radar on U-boat crews cannot be overstated. Submarine service had always been dangerous, but at least in the early war years, U-boat men felt they had some control over their fate. A well-commanded boat with a skilled crew could hunt convoys successfully and return home. By 1943, that confidence had evaporated. U-boat crews sailed knowing that something invisible was stalking them, that they could be detected at any moment without warning, that the darkness and fog they once relied on for protection had become meaningless. German submariners began calling the Allied aircraft that hunted them Black Crows, ravens of death that could see in the dark. The stress became unbearable. Some U-boats returned to base with crews on the verge of psychological collapse, men who flinched at every sound, who saw Allied destroyers in every shadow. The average life expectancy of a U-boat crew member dropped from months to weeks. Of the roughly 40,000 men who served in the German submarine service during World War II, approximately 30,000 died, a casualty rate of 75%, the highest of any German military branch. Yet the technology itself was morally neutral. Radar was simply a tool, a means of detecting electromagnetic radiation reflected off metal objects. What made it transformative was how it was applied, how tactical doctrine evolved around it, and how the men operating it learned to extract every advantage from this new capability. The best radar operators developed an almost intuitive sense for their equipment, understanding how atmospheric conditions affected propagation, how different targets produced different return signatures, how to filter out clutter and focus on genuine threats. The integration of radar with other intelligence sources created synergies that multiplied its effectiveness. Ultra-intelligence from decrypted German naval communications provided strategic warning of U-boat concentrations, allowing convoys to be routed around wolf packs or enabling support groups to be sent to threatened areas. High-frequency direction finding, called HFDUF, could detect and locate U-boat radio transmissions, providing tactical warning that submarines were nearby. Radar then became the tool that converted that warning into precise targeting information, allowing escorts to intercept submarines before they reached attack positions. The command and control implications were equally significant. Radar allowed escort commanders to maintain precise formation, keeping even in darkness or poor visibility, ensuring that the defensive screen around a convoy remained intact. It enabled coordinated tactics that would have been impossible relying on visual signals alone. Multiple ships could prosecute simultaneous attacks from different directions, guided by radar navigation and communication, overwhelming a submarine's ability to evade. The technical evolution continued throughout the war. Later radar variants incorporated plan position indicator displays that showed all contacts on a map-like presentation, making tactical situations easier to comprehend at a glance. Automatic tracking systems reduced operator workload, improved signal processing, enhanced the ability to detect small targets in heavy clutter. Each increment brought practical advantages that translated into more U-boats detected, more attacks successfully prosecuted, more convoys defended. The relationship between technological capability and tactical doctrine became a subject of intense study by operational research scientists embedded with naval commands. These analysts applied statistical methods and rigorous data collection to questions that had previously been addressed through intuition and tradition. They quantified the relationship between radar detection range and successful interceptions. They identified optimal search patterns. They calculated the probability of detection under various sea state and weather conditions. Their work transformed naval operations from an art into a science, or at least introduced scientific rigor into the art of war at sea. One critical insight from operational research involved the allocation of radar-equipped escorts within convoy screens. Early doctrine distributed escorts evenly around the convoy perimeter. Analysis showed that submarines attacked preferentially from certain angles based on convoy course, time of day, and tactical situation, concentrating radar-capable escorts in high-threat sectors while accepting some risk in lower-threat areas significantly improved overall convoy defense. This kind of nuanced, data-driven tactical evolution gave the Allies compounding advantages that German commanders struggled to counter. The human dimension remained central, despite increasing technological sophistication. Outstanding radar operators gained reputations that spread through the escort groups. Ships competed to recruit skilled operators. The best could distinguish between a surfaced submarine and a fishing vessel at extreme range, based on subtle differences in radar return characteristics. They could maintain situational awareness with multiple contacts, prioritizing threats and cueing teammates effectively. Their expertise represented the crucial link between technological potential and operational effectiveness. Without skilled operators, even the best radar was just an expensive paperweight. The phenomenon of technological determinism versus human agency played out in real time in the Atlantic. Did radar win the Battle of the Atlantic, or did skilled operators using radar win it? The question reveals a false dichotomy. Technology enabled new tactics, but tactics had to be developed, refined, and executed by humans under stress. Radar provided information, but humans had to interpret that information and make decisions. The most successful escorts were those where technology, training, experience, leadership, and crew cohesion all aligned. Removing any single element degraded effectiveness significantly. The tactical revolution enabled by radar manifested in increasingly sophisticated convoy defense strategies that transformed the Atlantic from a shooting gallery where submarines picked off merchant ships almost at will into a contested battle space where U-boats fought for survival. The integration of centimetric radar with other technologies, ASDIC, direction finding, code-breaking intelligence from Ultra, improved depth charges, and ahead-throwing weapons like Hedgehog created a layered defense system that left submarines with fewer and fewer options for successful attack. Captain Frederick John Walker, arguably the most successful anti-submarine warfare commander in history, exemplified how radar could be integrated into aggressive hunting tactics. Walker commanded the 2nd Support Group, a specialized submarine hunting force that operated independently of convoys, racing to areas where U-boats were known to be concentrated. His ships carried the latest radar equipment, and Walker trained his crews relentlessly in its use. Walker developed the creeping attack, a tactic that used radar to position ships precisely for coordinated attacks on submerged submarines. One ship would hold ASDIC contact on the submerged U-boat, while another approached silently at slow speed, guided by radio instructions and radar navigation to deliver a depth charge attack from an unexpected direction. The technique required precise ship handling, excellent communication, and absolute trust in the radar navigation system. it was devastatingly effective. Walker's group sank 15 U-boats in one 12-month period, an extraordinary record that earned him a reputation bordering on legend among both Allied sailors and German submariners. Aircraft integration proved equally critical. Coastal Command aircraft equipped with ASV Mark III radar could sweep vast areas of ocean, detecting surfaced submarines and either attacking immediately with depth charges or homing surface ships onto the contact. The development of the Lee light, a powerful searchlight mounted on aircraft that could illuminate a submarine at the last moment before attack, combined with radar to create a nearly unstoppable combination. Radar would detect the submarine at long range, allowing the aircraft to approach undetected. At the last moment, flying at wave-top height, the pilot would switch on the Lee light, flooding the submarine with blinding white light and giving the U-boat crew just seconds to react before depth charges rained down. The tactical playbook expanded rapidly as operational experience accumulated. Escort commanders learned to position their most radar-capable ships at specific points in the convoy screen where submarine attacks were most likely. They developed radar-assisted night encounter tactics, using the equipment to maneuver ships into optimal attacking positions before the submarine even knew it had been detected. They learned to recognize the distinctive radar signature of a U-boat running on the surface versus a submerged submarine with just its schnorkel mast exposed versus a fully surfaced boat charging batteries. The Americans, entering the Battle of the Atlantic in force in 1942, brought their own innovations. American destroyer escorts, produced in vast numbers by American shipyards, came equipped with excellent radar systems from the beginning. American naval architects designed these ships with radar integration in mind, placing antennas for optimal coverage and protecting sensitive equipment from weather and battle damage. The American SG surface search radar became one of the war's most reliable systems, renowned for its range and precision. Training programs evolved to match the technology. The British established HMS Philanti as a specialized radar school where escort commanders and their operators could practice in simulated conditions. Mock battles using radar against friendly submarines playing the role of U-boats allowed crews to develop skills without the lethal consequences of mistakes. The Americans created similar facilities, eventually training thousands of radar operators who spread throughout the fleet, bringing standardized techniques and shared understanding. But perhaps the most important solution was conceptual rather than technical. The recognition that radar wasn't a magic bullet, but a tool that required intelligent application, constant maintenance, and integration with all other available sensors and weapons. The escorts that achieved the highest success rates were those whose captains understood this principle, who cross-trained their crews, who fostered cooperation between radar operators, ASDIC operators, lookouts, and weapons crews, creating teams rather than collections of specialists. The doctrine of mutual support evolved significantly as radar capabilities improved. Escort groups developed standard procedures for radar-assisted searches, with ships positioned to provide overlapping coverage and eliminate blind spots. When one ship detected a contact, others would be vectored to prosecute from optimal angles, creating situations where the submarine faced threats from multiple directions simultaneously. This coordination was only possible because radar provided precise position information that could be shared via radio, allowing commanders to build a common tactical picture. Canadian escorts, which formed a substantial portion of mid-ocean escort forces, became particularly adept at radar-assisted operations. The Royal Canadian Navy expanded enormously during the war, growing from a handful of vessels to hundreds of corvettes and frigates. These ships and their crews, though often derided as less professional than their British or American counterparts, developed into highly effective submarine hunters. Canadian corvettes, small and uncomfortable but equipped with excellent radar, became the workhorses of convoy defense, their operators gaining hard-won expertise through brutal experience in the North Atlantic. The introduction of escort carriers, small aircraft carriers that could accompany convoys and provide air cover in mid-ocean, multiplied radar's effectiveness. Aircraft from these carriers, guided by ship-based radar to areas where submarines were suspected or detected, could search vast ocean areas and prosecute contacts that surface ships alone might never find. The combination of surface radar, airborne radar, and coordinated attacks from both aircraft and ships created a tactical environment where U-boats had nowhere to hide. Statistical analysis conducted by operational research scientists revealed patterns that improved radar employment. They discovered optimal search patterns, identified the most effective radar settings for different sea conditions, and quantified the relationship between detection range and tactical advantage. This scientific approach to naval warfare, using data to drive tactical evolution, was itself innovative, applying rigorous analysis to problems that had previously been addressed through experience and intuition alone. The human factor remained paramount despite technological advances. Outstanding radar operators developed reputations within the escort groups, their skill and judgment trusted implicitly by their commanders. These operators could detect contacts at extreme range, distinguish between different target types with uncanny accuracy, and maintain situational awareness even in confused tactical situations with multiple contacts and high sea states. Their expertise, built through months or years of continuous operations, represented institutional knowledge that training schools could only partially replicate. Maintenance and reliability engineering became critical disciplines. Radar sets that didn't work when needed were worse than useless. They created false confidence and diverted resources. Escort groups developed rigorous testing protocols, with radar sets exercised daily and problems addressed immediately. Supply chains were established to ensure spare parts reached ships at sea. Technical representatives from radar manufacturers sometimes sailed with escort groups to provide expert maintenance support and gather feedback for design improvements. The evolution of night fighting tactics deserves particular attention. Before radar, night combat at sea was chaotic and unpredictable, dominated by chance encounters and confusion. Radar transformed night operations into precise, controlled engagements where the side with better sensors held overwhelming advantage. Escorts could detect surfaced U-boats at several miles range, close to optimal firing position, while tracking the target continuously, and engage with guns or depth charges with confidence that they were attacking an enemy rather than a friendly vessel or neutral. The Germans attempted to develop countermeasures beyond simple radar warning receivers. They experimented with radar-absorbent coatings, modified conning tower shapes to reduce radar cross-section, and developed tactics for rapid crash dives when radar warning receivers indicated illumination. Some U-boats were equipped with anti-aircraft guns and instructed to remain on the surface and fight it out with attacking aircraft rather than diving. This desperation tactic sometimes worked against single aircraft, but proved suicidal when multiple attackers coordinated their approach using radar. The development of schnorkel systems, which allowed submarines to run diesel engines while submerged with only a small mast breaking the surface, represented Germany's most effective technical countermeasure to Allied radar. Schnorkeling boats were much harder to detect, as the radar cross-section of a mast was tiny compared to a surfaced submarine. However, schnorkeling significantly reduced operational effectiveness. Submerged speed was slow, battery capacity limited endurance, and the submarines couldn't observe the sea surface effectively to locate targets. U-boats forced to rely primarily on schnorkel operation became defensive rather than offensive weapons, more concerned with survival than sinking ships. By late 1943, the balance had shifted decisively. Convoy losses plummeted while U-boat casualties soared. The famous Black May of 1943 saw 41 U-boats destroyed, losses so severe that Dönitz temporarily withdrew his submarines from the North Atlantic. Though U-boats continued operating throughout the war, they never again posed the existential threat they had in 1940 and 1941. The turning point had multiple causes, but radar stood at the center of the transformation. The strategic implications extended beyond the immediate tactical victories. The security of the Atlantic sea lanes enabled the massive buildup of American forces in Britain necessary for the invasion of Europe. Millions of tons of supplies, hundreds of thousands of troops, thousands of aircraft and vehicles all crossed the Atlantic, protected by escorts whose radar gave them decisive advantage over submarines. Without that protection, Operation Overlord would have been impossible. In this sense, radar in the Atlantic wasn't just a tactical enabler, it was a strategic prerequisite for Allied victory in Europe. The radar revolution in anti-submarine warfare raises profound questions about the nature of technological advantage in military conflict and the human dimension of war in an era of increasing mechanization. Was the Allied victory over the U-boats fundamentally a technological triumph, Or did technology simply enable superior strategy, tactics, and operational execution? The answer is complex and reveals tensions that remain relevant in contemporary warfare. Some historians emphasize the technological determinism narrative. The Allies developed better radar faster, and this technological superiority inevitably led to victory in the Atlantic. This perspective has merit. The cavity magnetron was indeed a revolutionary invention, and German scientists never quite matched Allied capabilities in centimetric radar during the war years. The Germans invested heavily in submarine technology, developing Type 16 boats with revolutionary underwater performance, but these arrived too late to affect the outcome. If the technological race had gone differently, if Germany had developed effective centimetric radar first, or had broken the Allied monopoly on high-powered magnetrons, the Battle of the Atlantic might have ended very differently. However, this technological determinism overlooks critical factors. The Allies didn't just have better radar, they had better doctrine for using it, better training programs, more ships to mount it on, better integration with air power, and, crucially, access to German communications through ultra-intelligence. The famous Black May of 1943, when 41 U-boats were sunk in a single month and Dönitz was forced to withdraw his submarines from the North Atlantic, resulted from the convergence of multiple factors. Radar was essential, but so was the presence of escort carriers providing air cover in mid-ocean, improved depth charges, better convoy organization, and intelligence that allowed convoys to be routed around wolfpack concentrations. The moral dimension of this technological warfare merits examination. Radar operators, safe in their ship's chart rooms watching glowing screens, were instrumentalizing violence, reducing human beings to blips of light to be tracked and destroyed. This distancing effect, where killing becomes abstract and distant, would become a defining characteristic of modern warfare. Yet those radar operators were defending merchant sailors from submarine attack, protecting the lifeline that kept Britain in the war. The young German submarine crews they helped destroy were themselves trying to starve Britain into submission, targeting civilian merchant vessels carrying food and fuel. Some historians have compared the Allied submarine campaign against Japan, where American submarines ultimately sank nearly 5 million tons of Japanese shipping, with the German campaign in the Atlantic, noting that both targeted merchant vessels and civilian logistics. The distinction lies partly in international law and partly in strategic context. Germany was attempting to strangle an island nation into submission. The Allies were fighting to defeat an aggressive totalitarian regime. Both campaigns were brutal and killed thousands of merchant sailors. The radar technology that helped defeat German submarines in the Atlantic was later used against Japanese submarines in the Pacific, though with less strategic impact, since Japan's submarine doctrine focused more on attacking warships than merchant vessels. The strategic bombing debate offers an interesting parallel. Both strategic bombing and anti-submarine warfare aim to destroy the enemy's capacity to wage war by attacking economic targets and logistics. Both raised questions about the morality of targeting systems that inevitably involved civilian casualties. Merchant sailors, though not combatants in the traditional sense, crewed the ships that fed armies and supplied war industries. Their deaths were tragic, but within the logic of total war, legitimate targets of military action. The post-war development of radar technology into civilian applications raises questions about military research and dual-use technologies. The cavity magnetron designed to destroy submarines became the heart of the microwave oven. Radar systems developed for finding U-boats evolved into air traffic control, weather forecasting, and maritime safety systems. The enormous investment in wartime radar research, funded by desperate military necessity, created technologies that fundamentally altered civilian life. Would this research have happened without war? Possibly, but certainly not at the same pace or scale. The experience of radar operators themselves provides insight into the human adaptation to technological warfare. Many of these young men entered the war with minimal technical education and emerged as skilled practitioners of sophisticated electronic warfare. They had to develop new cognitive skills, interpreting abstract visual data, maintaining situational awareness across multiple information sources, making split-second decisions with incomplete information. These skills, largely unprecedented before the war, would become fundamental to modern military operations and eventually to civilian life in the information age. One cannot ignore the tremendous cost of this technological learning curve. Ships were lost because radar wasn't available, or wasn't working, or wasn't properly used. Men died because of equipment failure, operator error, or simple bad luck. The early months of radar deployment saw numerous friendly fire incidents, with escorts attacking each other or neutral vessels because operators misidentified contacts. The technology saved countless lives over time, but the path to effective implementation was marked by painful lessons learned through tragedy. The asymmetry between Allied and German radar capabilities also reflected broader strategic differences. The Allies, with access to superior industrial capacity and scientific infrastructure, could afford to pursue multiple parallel development tracks, fielding various radar types optimized for different purposes. Germany, increasingly resource-constrained and under constant bombardment, struggled to maintain research programs while also supporting urgent production needs. German scientists made remarkable achievements given their circumstances, but they were fighting an uphill battle against enemies with deeper reserves of talent, funding, and manufacturing capability. The radar war also highlighted the importance of operational security and intelligence. The Germans knew the Allies had radar, but consistently underestimated its capabilities and effectiveness. German intelligence failures in assessing Allied technology gave the Allies crucial time to build and exploit their advantage. Conversely, Allied intelligence about German radar development, gathered through various means, including captured equipment and interrogated prisoners, helped guide countermeasure development and tactical evolution. The question of how individual lives should be valued in the calculus of technological warfare remains troubling. Each U-boat sunk represented typically 40 to 50 young men killed, drowned in cold Atlantic waters, or crushed by pressure as their boat plunged beyond its collapsed depth. Many were teenagers or men in their early 20s, conscripts serving a totalitarian regime, but nonetheless human beings with families, hopes, and dreams. The radar operators who helped kill them were also young men, doing their duty in a war they didn't start. The moral weight of these deaths, however distributed across technologies and chains of command, ultimately fell on individuals who had to live with what they'd done. Yet counterfactual analysis suggests that without radar and the other technologies that defeated the U-boat threat, Britain might well have been forced out of the war. If the Atlantic lifeline had been severed, if merchant ship losses had continued at early war rates, the strategic position would have become untenable. The technology that killed German submariners also saved merchant sailors, enabled the buildup of forces that eventually liberated Europe and contributed to the defeat of fascism. Within this framework, the development and use of radar technology appears not just justified, but necessary. The precedent set by radar development, massive government investment in applied physics and engineering, close cooperation between military and civilian scientists, rapid transition from laboratory to battlefield, established patterns that would define post-war military research and development. The Manhattan Project, jet aircraft, guided missiles, and eventually computers and the internet all followed similar paths, with military necessity driving innovation that eventually found civilian applications. Whether this represents the optimal model for technological development or a distortion of scientific priorities toward destructive purposes remains debated. The radar experience also demonstrated the critical importance of alliance cooperation and technology sharing. Britain's decision to share the cavity magnetron with the United States made it a moment of desperate vulnerability, enabled American industrial might to produce radar systems in quantities neither nation could achieve alone. This partnership became a template for subsequent Allied cooperation, from nuclear weapons to space exploration to contemporary defense technology development. The willingness to share sensitive military technology with trusted allies, despite security risks, proved strategically advantageous. The ethics of technological surprise deserves consideration. The Allies possessed for a time a sensor system the Germans couldn't detect or counter, giving them what amounted to an unfair advantage in tactical engagements. Is such asymmetry morally problematic, or simply the natural result of superior innovation? Military ethics generally accepts that combatants have no obligation to fight on equal terms. Indeed, the whole point of military research and development is to create advantage. Yet the one-sidedness of radar-equipped escorts hunting submarines that had no idea they were being tracked raises questions about whether technological asymmetry can become so extreme as to constitute something other than legitimate warfare. These philosophical questions aside, the practical reality is that radar represented a legitimate military technology developed in response to a genuine threat. It was used to defend merchant shipping carrying civilian populations' food and war supplies, and to sink submarines engaged in attacking those vessels. Within the framework of total war between industrialized nations, these actions fall clearly within acceptable bounds. The tragedy lies not in the technology or its use, but in the war itself, the political failures that led to conflict, and the human cost of that conflict once begun. The Type 271 radar set and its successors represented far more than just a new piece of military equipment. They embodied a fundamental shift in how humans wage war, how they perceive and interact with their environment, and how technology mediates the relationship between intention and outcome. When that radar operator on a foggy Atlantic night in 1943 detected a U-boat at 4,000 yards and guided his ship to the kill, he was participating in a transformation that would echo through the decades to come, shaping everything from Cold War naval strategy to the air traffic control systems that safely guide millions of flights every year. The Battle of the Atlantic turned definitively in the Allies' favor in the spring of 1943, and while many factors contributed to this turning point, radar technology stood at the center of the transformation. The statistics tell a stark story. In the first quarter of 1943, U-boats sank nearly 500,000 tons of Allied shipping, while losing 15 submarines. By the third quarter, sinkings of Allied ships had dropped to less than 200,000 tons, while 55 U-boats went to the bottom. The hunters had become the hunted, and the electromagnetic spectrum had become the new domain of warfare. Admiral Dönitz recognized defeat when he saw it. His post-war memoirs acknowledged that the technological balance shifted against Germany, and that his submarines could not overcome the combination of Allied detection systems, weapons, and operational methods. He withdrew U-boats from the North Atlantic, experimented with different tactics, pushed for revolutionary submarine designs that might restore the balance, but never regained the initiative. The young men who crewed his submarines paid the price. By war's end, the U-boat service had suffered casualties proportionately worse than any German combat arm, worse even than the Waffen-SS or the Luftwaffe fighter force. The legacy of the radar revolution extends far beyond the military sphere. The scientists and engineers who developed wartime radar systems returned to civilian life and applied their knowledge to peaceful purposes. The MIT Radiation Laboratory, which had been the center of American radar research during the war, spawned technologies and companies that would define the post-war electronics industry. The skills learned by radar operators, data interpretation, systems thinking, the ability to extract meaning from abstract displays, became valuable in the emerging information economy. Perhaps most significantly, radar established the template for how technological superiority would be pursued in subsequent conflicts. The Cold War became, in many ways, a competition between sensor systems and countermeasures, between detection capabilities and stealth technologies. The logic was the same as the Atlantic U-boat war: see without being seen, detect without being detected, strike before the enemy knows you're there. Every stealth aircraft, every submarine sonar system, every electronic warfare suite traces its conceptual lineage back to those first centimetric radar sets rotating atop British destroyer masts in the dark Atlantic. For the individual sailors who survived the Battle of the Atlantic, radar was simpler and more immediate. It was the thing that kept them alive. Merchant sailors who made repeated crossings in convoy saw the difference radar made in their survival odds. Escort crew members understood that the metal box with its glowing screen and rotating antenna represented the difference between blindly searching thousands of square miles of ocean and knowing exactly where the enemy was lurking. To them, the technology wasn't abstract. It was the tool that brought them home. The story of radar in the Atlantic demonstrates how technology, strategy, courage, and sacrifice interweave in the crucible of total war. It shows how innovation can decisively shift the balance in a conflict that seemed locked in stalemate. It reveals the tremendous human cost of technological learning, the lives lost to equipment failure, operator error, and the time needed to translate laboratory success into battlefield effectiveness. It illustrates how determined adversaries can adapt and counter-adapt, creating cycles of innovation and response that drive rapid technological evolution. Most importantly, it reminds us that technology alone never wins wars. The cavity magnetron was a brilliant invention, but it required mass production, effective distribution, comprehensive training programs, tactical innovation, operational integration, and thousands of skilled operators working under brutal conditions to translate that invention into strategic impact. Victory in the Atlantic required not just better sensors, but better strategy, better logistics, better intelligence, numerical superiority, and the will to persevere through years of losses and setbacks before the tide finally turned. The Germans called it Hexengerät, the witch's device. Allied sailors sometimes called it the eye that never sleeps. Historians recognize it as one of the decisive technologies of World War II. But perhaps the best description comes from a British radar operator who, when asked decades later about his wartime service, simply said, "We made the night transparent. We took away their darkness, and without darkness, the submarines couldn't survive." That sentence captures the essence of what radar accomplished in the Battle of the Atlantic. For millennia, darkness had protected ships and men who wished to move unseen. The ocean at night had been a vast empty blackness, where visibility measured in yards and detection relied on chance sightings or the sound of engines. Radar stripped away that protective darkness, making the invisible visible, turning chaos into order, transforming blind searching into precise hunting. When the last U-boat surrendered in May 1945, the age of submarine warfare as Dönitz had practiced it was over. Future submarines would operate primarily underwater, using nuclear power and advanced sonar systems, engaged in a different kind of hide-and-seek game in the ocean depths. But the surface submarine, the wolf of the Atlantic that stalked convoys under cover of darkness, had been hunted to extinction by a technology that made darkness irrelevant. The legacy lives on in every radar screen, in every ship, aircraft, and air traffic control tower in the world. Every time a pilot relies on weather radar to avoid a storm, every time air traffic control vectors an aircraft to a safe landing in fog, every time a ship's radar prevents a collision at sea, the descendants of that wartime technology continue their work, no longer finding submarines to destroy, but finding aircraft to guide safely home, finding obstacles to avoid, finding certainty and uncertainty. The young men who first operated those temperamental revolutionary systems, adjusting vacuum tubes, interpreting glowing traces, guiding their ships toward contacts in the darkness, have mostly passed away now. But their contribution endures, not just in the historical record of battles won and convoys protected, but in the fundamental transformation they helped achieve in humanity's relationship with technology, detection, and the electromagnetic spectrum. They taught the world that invisible waves could reveal hidden enemies, that mathematics and physics could be weaponized as effectively as steel and explosives, and that in modern warfare, the side that sees first often wins decisively. In the end, radar in the Battle of the Atlantic represents a case study in how technological innovation, properly developed and effectively deployed, can break strategic stalemate and shift the balance of power in existential conflicts. It demonstrates the critical importance of research and development, of investing in emerging technologies even when their practical applications remain unclear, of maintaining scientific and industrial capacity that can be mobilized in times of crisis. Most fundamentally, it shows that in the terrible crucible of total war, the civilization that can most effectively mobilize its scientific genius, its industrial capacity, and its human resources toward military ends holds a decisive advantage, an advantage that radar helped the Allies achieve and that contributed meaningfully to the defeat of Nazi Germany and the preservation of democratic civilization in the face of totalitarian aggression. The Atlantic became a laboratory for technological warfare, where theory met practice under the most demanding conditions imaginable. The lessons learned there about the importance of operator training, the necessity of continuous improvement, the value of integrating multiple sensor systems, the criticality of maintenance and logistics, informed military thinking for generations. Modern network-centric warfare, with its emphasis on shared situational awareness and sensor fusion, represents the culmination of concepts first explored in those desperate convoy battles. The human stories behind the technology deserve remembrance. The radar operator who stayed at his post for 12 straight hours during a convoy battle, eyes burning from staring at the cathode ray tube, tracking multiple contacts while his ship maneuvered violently in heavy seas. The radar mechanic who worked through the night in a pitching, spray-soaked compartment to repair a critical component before dawn, knowing that daylight would bring renewed submarine attacks. The convoy commodore who trusted his radar information enough to make course changes that seemed counterintuitive, but that steered his charges away from waiting wolf packs. The U-boat commander who, realizing that his boat had been detected by some invisible means, chose to surface and fight rather than dive into a depth charge barrage he knew was coming. Each of these individuals, and thousands like them, played their part in a technological drama that shaped history. The ethical implications of technological warfare continue to resonate. Radar made killing more efficient, but also more abstract, beginning a trend that has continued through guided missiles, drone strikes, and cyber warfare. The radar operator who detected a submarine and guided his ship to attack might never see the enemy vessel, never witness the human cost of his actions. This distancing from the consequences of violence raises questions about moral responsibility, about whether technology that makes killing easier also makes it morally more problematic, or whether the just cause of fighting totalitarian aggression justifies whatever means prove effective. What remains indisputable is that radar technology, combined with human skill, determination, and sacrifice, helped win the Battle of the Atlantic. That victory kept Britain in the war, enabled the build-up for D-Day, and contributed to the eventual Allied triumph in Europe. The invisible beams that bounced off submarine conning towers in the darkness changed the course of history, proving that sometimes the most powerful weapons are those you cannot see, and that in war the ability to perceive the enemy before he perceives you can be more valuable than any gun or bomb. The transformation from laboratory curiosity to war-winning technology took less than 3 years, a testament to what desperate urgency, massive resources, and brilliant minds can accomplish when focused on a critical problem. From Randall and Boot's cavity magnetron in February 1940 to operational Type 271 radar sets sinking U-boats in 1941, the timeline was astonishingly compressed. This rapid innovation cycle established patterns that would characterize military technology development throughout the Cold War and beyond, where the pace of advancement became itself a strategic factor. The collaborative nature of the radar development effort also deserves emphasis. British physicists invented the cavity magnetron. American engineers turned it into manufacturable products. Canadian, British, and American naval officers developed tactics to exploit it. Operational research scientists analyzed its effectiveness and recommended improvements. Thousands of sailors learned to operate and maintain it under combat conditions. This distributed, collaborative innovation, spanning nations, disciplines, and military-civilian boundaries, proved far more effective than any single organization could have achieved. Looking back from our modern technological perspective, where radar is ubiquitous and taken for granted, it's easy to underestimate how revolutionary this technology seemed to those who first encountered it. Imagine being a destroyer captain in 1941, having spent months searching blindly for submarines at night, suddenly being told that a new box installed on your ship could see invisible electromagnetic waves bouncing off metal and tell you exactly where enemy submarines were located. It must have seemed like magic, and to some extent the physics underlying radar was sufficiently complex that many operators never fully understood how their equipment worked. They didn't need to understand the theory. They needed to interpret the display and act on the information it provided. This brings us full circle to the human element that underlies all technological warfare. Radar was revolutionary, but it was wielded by human beings making human decisions under inhuman stress. The technology expanded what was possible, but humans determined what was actual. The radar operator who distinguished between a false return and a genuine submarine contact. The escort commander who positioned his ships based on radar information. The convoy commodore who trusted radar enough to alter course into weather that seemed suicidal. The aircraft pilot who followed a radar contact down through clouds to find a submarine and attack it. Each of these decision points involved human judgment, human courage, human expertise developed through hard experience. The witch's eye saw far and saw truly, but it was human eyes that interpreted its vision, human hands that acted on its revelations, and human lives that were saved or lost based on those actions. Technology transformed the battlefield, but humans fought the battle. That fundamental truth underlies all of military history and remains relevant today as we contemplate autonomous weapons, artificial intelligence, and the increasing role of technology in warfare. The tools change, but the human dimension endures. For better and for worse, it is humans who decide how tools are used, and humans who bear the consequences of those decisions. In the final accounting, the radar revolution in the Battle of the Atlantic stands as one of history's most successful applications of science to warfare, one of the clearest examples of how technological advantage can decisively influence strategic outcomes, and one of the most significant technological developments of the 20th century. Its legacy extends far beyond the military sphere into every aspect of modern life touched by wireless technology. But for the men who lived through it, the radar operators and the U-boat crews, the escort commanders and the merchant sailors, it was simply the crucible in which their fate was determined, where invisible beams of electromagnetic energy meant the difference between life and death, between victory and defeat, between a world preserved and a world lost to darkness.